All right, ladies and gentlemen, welcome back to another round. We're going to jump right into this. I don't want to take up too much of your time here, and I've got a little bit to place into your minds today. So we're going to take a look today at TBO. Really, it's just how are we going to draw these covalent molecules in three-dimensional space, and I've circled something and written and starred it here on the page, and I need you to write it really big across your page, is don't forget TBO checks octets. So don't forget TBO checks octets. Yes, when you saw TBO doing the TBO, he was literally looking down in his pocket, looking over his chemistry homework, checking his covalent compounds and checking them for octets. TBO checks octets. All right? So keep that in mind as we run through this. Okay. So let's start with what a covalent bond is. So remember, covalent bonds, they actually share electrons. All right, there's a sharing going on. There's no transfer. It can actually go back and forth from any particular element. It's based on electronegativity differences. And so what we really want to know is, what does that look like? So what does sharing electrons actually look like? And so before we get on, I want to remind you of a couple of things. The first off, valence electrons are the ones involved in bonding, right? The next one, a full S or P valence shell represents a low energy state, right? There's some sort of stability there, but really what happens is, because everything in nature tends towards its lowest energy state, a full S and P valence shell represent a low energy state. And so that's what we're going to use to drive how we're going to place these atoms around each other, and how we're going to connect them with their electron sharing, is we're going to try and fill up that valence shell, right? In other words, we are going to give everything an octet. An octet is a full S and P valence shell. All right, and so what TBO does, it does allow us to place in all those valence electrons properly. Okay, so first I want to get to some generalities, and you probably won't understand these just yet. And so a couple of generalities. The first one is for hydrogen. Hydrogen will never be a central atom, right? It'll never be a central atom, and it'll never have more than a single bond. So it'll never have more than a single bond, and it'll never be a central atom. All right? And so those are your generalities for hydrogen. The next set of atoms that I want you to know is CNOPs. Now, CNOPs are 5 elements that can participate in double bonds. And I'm going to go ahead and write this one out. And I guess you could say that they also could participate in single bonds. And so what I mean by that literally is that I can have a carbon molecule single bonded to another carbon molecule, right? I've got one line shown there. And what I say is that this is a sigma bond. A single bond is a sigma bond, and that's the symbol for sigma. The next one is I could have a carbon-carbon double bond. And what it means is that now I have a sigma bond, but I also have a pi bond. And so the second bond that appears there is actually your pi bond. And then on the last one, I've got a carbon-carbon triple bond, which can also happen. And yep, you're right, I've got a sigma, and then I've got a pi bond, and I've also got another pi bond. So your sigma bond is your very first single bond that occurs between two elements. Your pi bond is an overlapping of some other orbitals so that we can get a double bond and a triple bond, and CNOPs are the 5 elements that participate in double and triple bonds. All right, and so now we get into exactly what is TBO. Well, it's an acronym, so it's T minus B minus O, and that's why it's T minus BO. All right, and so the T stands for my total valence electrons. So your T is your total valence electrons. Your B is your total electrons involved in sigma bonds. So this is the little sigma symbol, right? And so please understand the bonding are the electrons involved in sigma bonds. Each sigma bond represents 2 electrons because there's a shared pair of electrons there. So each sigma bond is 2 electrons. And then the O is my outer lone pair electrons. And so these are my outer atoms. I'm looking at the lone pairs, the electrons that are not involved in a bond but just exist around the atom itself. And then after I take my total, right? This is my total. Total minus my bonding electrons minus my outer lone pair electrons. My leftovers go on the central atom. All right, and so now what I'm going to do is I'm going to show you this AXE, right, that y'all have been memorizing. If I've got A with X, 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 and then I'm going to have one lone pair of electron right there. So with this, my A represents my central atom, X represents my outer atoms, and I use a subscript to tell me how many they are. And then this guy right here, that is a lone pair that exists on the central atom. I'm going to use a capital E to designate that, and then I'm going to tell me how many there are there. So notice there's 2 electrons, but there's only 1 pair of electrons. And so this is called the AXE designation, and we're going to use that to determine our molecular geometries. And so the AXE molecular geometry of this one would actually be trigonal pyramidal. All right? Okay, so now let's do a couple of examples. Okay, so the first example I'm going to take a look at is actually NH3, or ammonia. And so what we'll do is, again, just total minus bonding minus outer. Now, my total valence electrons, hopefully you have a periodic table here. I'm just looking at group numbers. Nitrogen has 5 valence electrons, and each hydrogen has 3. But I've got 3 hydrogens there, so I have a total of 8 valence electrons that I need to place. I'm going to put the nitrogen in the center, right? And don't think and freak out about this. Generally speaking, the first element is going to go in the center of the atom unless it's a hydrogen. Remember, hydrogen can't be there. And so what I've done is I've placed my outer atoms attached to my central. Notice I've got 3 single bonds there. Those are my sigma bonds. So those represent bonding electrons. And then for my outer atoms, remember, I don't get any more than a sigma. If you look at hydrogen, it's in the first period. Hydrogen will never have an octet. Hydrogen will never have an octet, so it never gets any outer lone pairs. So now I've got 8 minus 6, I've got 2 left over, and remember my leftovers go on the central atom. The AX notation for this would actually be A, X3, E1. Yes, I know, we just drew that. Okay, so now the next one that we're going to take a look at is we'll look at water, or H2O. Again, I'm going to do T minus B minus O, check for octet. Now, I did check for the octets at the end. Notice, in octet, I've got 2, 4, 6, 8 electrons around nitrogen, and hydrogen is actually stable with only 2 electrons. So here, my total, oxygen has 6 valence electrons, hydrogen's got 2, so again, I've got 8 valence electrons. Oxygen has to be in the center here because, remember, hydrogen cannot be a central atom, according to my generalities. So I've just placed 4 electrons in my sigma bonds, and again, I don't have any outer electrons, so I have 4 left over. Well, those leftovers go on the central atom, right? And then I'm going to check the octets. Again, I'm checking the octet of my central atom. I got 2, 4, 6, 8. I'm done. And so my designation on this would be AX2, E2. And you can come up with the molecular geometry for that. All right. My next one that I'll look at, and this will be the last one that we do today, is actually carbon dioxide. And so again, TBO, or TBO, I'm going to do, carbon has 4 valence electron, each oxygen has 6, that's 12, that would be 16 valence electrons to place. I'm going to put carbon in the center, and I'm going to attach each oxygen here, right? So I've put 4 electrons in sigma bonds, and then for my outers, I actually am going to need to fill the octet of my outer atoms here. And so notice I have to place 6 electrons around each oxygen. This sigma bond, these 2 electrons count for both the central atom and the outer. So I've got 2, 4, 6, 8 around the oxygen, 2, 4, 6, 8 around the other oxygen. But remember, the O here is my lone pairs. So I've got 2, 4, 6, 8, 10, 12 out there, which means I've got 0 left over. So I don't put any back on the central atom. Now, there is an issue that exists here, because notice now when I go, and remember TBO checks octets, my carbon in the middle does not have an octet around it. And so here we go. Here's a rule that you're going to write down. I'm going to take a lone pair off of an outer atom, and I'm going to move it into a pi bond. I'm going to take a lone pair from an outer atom, and I'm going to move it into a pi bond. So those are gone, right? And so now I've got 2, 4, 6 around my carbon. I'm going to have to do it again. And so I take a lone pair off an outer atom, and I put it into a pi bond. So now 2, 4, 6, 8, those are gone. And so now my carbon dioxide molecule has an octet, 2, 4, 6, 8 molecule or electrons around it. If you redraw this over here, I'm just going to come over here and redraw this guy. You'll notice that the oxygens 2, 4, 6, 8 have an octet, 2, 4, 6, 8 octet, and then my carbon 2, 4, 6, 8. Everybody has an octet, everybody's stable, everybody's low energy state, and there we go, and we're good. All right? And then the shape for this would be AX2. And hopefully you know that that means that that's a linear molecule. And now, ladies and gentlemen, that's it. That's all we've got. So TBO is relatively simple. Just remember to check that octet at the end. If you have any questions, hopefully you got them written down. We can take care of those during class, or you can come to tutorials to get some extra help on that. But I will see you there.